Uh, Good morning. Let's start. Um, so today we will continue on formulations, specifically integer programming formulations, which I started off with on Wednesday, and I want to cover a few more ideas related to it. So modeling with integer programming is a little bit more nuanced than maybe typical LPs. I mean, LPs, of course, you also have to think about modeling, but integer programming models, the way you formulate problems is a more important. I mean, it's you have to be careful in the way you model things. Okay, and so I want to discuss that. And then just heads up, the following 2 weeks, we will talk about methods for solving integer programs. So I won't discuss any techniques as yet to solve it, but we will discuss methods. Okay. 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 Are there any questions before I get started? Like any queries from last class or any questions? Any, I don't know, philosophical questions on the topic or otherwise? Technical, that's fine too. Yeah. No? Okay. Okay. So we are doing integer programming formulations, and I won't recap everything that we did last time, but basically we saw that many binary decisions, yes no decisions, basically are modeled with integer programming. And more generally we can model things like, we can so just a recap. We saw things like binary decisions is clearly a 0 1 decision variable. Okay. We saw things like, if we have discontinuous values, discontinuity, discontinuous values, that's an integer, can be modeled using integer linear programming. We saw things like piecewise linear functions can be modeled using integer programming. We saw things like fixed costs can be modeled using integer programming. Okay. Trying to think about any others. So we saw several of these examples, and even things like, products of binary variables we saw can be modeled using by basically adding in some new binary variables. Okay, and this is not everything I covered, but I these are some of the main ideas that I covered last time. Okay, and then I showed you one example which was Sudoku. So so we saw an example which was Sudoku, where you can actually model finding a Sudoku solution as solving a integer feasibility problem. There was a question about, is there any objective function? No, there was no objective function. It was just to solve a set of linear equations in binary variables and to check if there was a solution to the problem. Okay. So I want to show you one more example today, and there are many examples of integer programming formulations. It turns out, depending on the type of applications you're working on, you will use them. So I will show you one example that I worked on specifically. This is related to the university. So here's a problem. So let me just go to the next slide, maybe. Okay. So here's a particular problem that it's an allocation problem. So okay. So here's an example. I just want to show you one more example of an IP formulation. So very often when you have allocation decisions, you're trying to allocate some task to somebody or some job to somebody. You often require, and that there are some complicating constraints, you require some integer programming formulations. So I don't know how much you know about, I mean, I know many of you have just joined the university, but at the university, we have we have, at least in the recent past, we had four different pillars. There's ESD and ASD and EPD and ISTD, and now there are some, there's some other undergraduate degrees. And one thing which happens in the university is you have to the all undergraduate students have to do something called a capstone project. Okay, what's a capstone project? It's a final year project which you probably have done during your undergraduate studies too somewhere. You work on some project. Typically, in any undergraduate program, you do some sort of project at the end of the course, near the last year. And at SUTD, it's designed in a particular way. Okay, so the way it's designed is you have to work in a multidisciplinary group. So because the university is high on tech and design and stuff like this, and not being very solo in their own disciplines, the capstone projects here, the undergraduate final year projects, which are primarily company driven, require students from different pillars to work together. That means some students from the ESD pillar, maybe some students from an EPD pillar, maybe they build robots and stuff like that. maybe the ESG students, do some optimization, simulation, and so on, but they come together to solve a problem. Okay. Okay. So what is the problem? The problem is there are students every year who come into the university. Maybe there are, let's say, 300 students, and there are projects, and the students have to be allotted to projects. And students might like similar projects. Uh, there might only be a few projects of certain types. So it's an allocation problem. Okay. So just to give you a sense, let's say I've got, there are students, let's say there are students one up to S. Okay. So these are students. Okay. And just to, roughly the scope of the problem, let's say at SUTD, maybe, I don't know, 300 students roughly. Okay. Okay. You have projects. Okay. What are these projects? These are company projects. Let's say 1 up to P. Okay. Typically, there are about, let's say, about 60 projects. Okay. So how do you get these? I'm sorry, roughly 60 projects. How do you get these projects? You get these projects by working with companies. So the university will work with the company. Let's say they work with, I don't know, let's say LTA. Okay, so Land Transport Authority gives them some projects to work on, which should be interesting for the undergraduate students to do, and multidisciplinary. Okay, and they will scope out this project. The faculty scope this out, and some people in the admin scope it out, and they create these projects. Each of these projects has some requirements. Okay, so every student comes from a discipline. Okay, I mean, every student has some expertise. Okay, so at SUTD, I mean, till recently there were basically 4 different expertise. Okay. Um, okay, now maybe there are 5, but let me just stick with 4. So these are disciplines. So what's a discipline? It's basically a pillar. Okay. At okay, roughly 4. So this is something like, you're an ESD student, you're an EPD student, or some, ISTD and ASD. So there are 4 basically. Okay. Okay. So there are 4 disciplines. Every student is of a discipline. Okay. So every student S has a discipline. Okay. So I mean, every student graduates from one particular pillar, so they have some expertise. Okay. Every project has a requirement of a certain number. So every project will require you to have a certain number of a lower bound. So let's say project P, the Pth project. Okay, this is capital P, this is small p. The Pth project has a lower bound which depends on the project, whichever project it is, and the discipline that you're interested in. So I'm going to index disciplines D from 1 up to capital D. So D is 4, students from 1 up to capital S. So let's say S is 300. Projects P from 1 up to capital P. Let's say P is 60. Okay. Every student is of a particular discipline, and every project requires students of a certain number of students of each discipline. Okay. So maybe it's a project, let's say, where there is no architectural aspect. So if, let's say, the discipline architecture D is equal to 4 represent architecture, and let's say this project does not involve any architectural component, the lower bounds and the upper bounds on the number of students will be 0. You want 0 students of an architectural project to be allotted to this project. Okay. So these are basically data which are scoped out by the company and the university. Okay. So they'll try to figure out, does this project have, what type of expertise does it require? And this can be figured out. And, very often you don't get precise numbers. I mean, if you get precise numbers, you can make the lower and upper bound to be the same. But, you might say between 2 and 3 students. If you think that the more students required, maybe between 4 and 5 students. Okay. Okay. Is that clear so far? What do you want to do? You want to allot students to projects, but students, you don't want to randomly allocate students to projects. You want students to be allotted to projects that they want to do. Okay. So you have to get student preferences into account. Okay. So one way you can do this is you basically show students the details of the projects and ask students to rank out the projects. Okay. And of course, you can ask the students to rank out all the projects which there is offered to their pillar, or maybe they choose their first 20 or first 15. Okay. So every student will give you a utility. Okay. Utility, let's say student S for project P, essentially tells you how utility of project P for student S. Okay. So think of this if you want like rankings. What is my top ranked project? Okay. And second ranked and so on and so forth. Maybe just to make these, we're going to set up a maximization problem. So let's say the utility is high. That means I like the projects. If my utility is zero, I don't like the project or I don't want to do the project. Okay. So is the setup clear? So this is the problem. Okay. You need to allocate 300 students to 60 projects across disciplines with specifications on the projects and taking students' expertise into account. How does the university solve this problem? What do you do? So it turns out for the past 5 to 10 years, the students basically an integer program is being solved to do this allocation. Okay. So you can basically write an IP to do this. Okay. So what do? You're going to have two sets of variables. So you're going to have a variable yp, which is going to be 0 or 1. 1, if project P is offered, okay, and 0 otherwise. Okay. So what happens is, suppose you have a project and maybe no student is interested in that project, then you may not want to offer that project. Every project that a company offers cannot be launched by the university because there's not enough interest from the students. There might be enough insufficient students, or there might be too many projects, or whatever reasons. So you have to figure out which projects you can actually offer based on interests. Okay. So that's a binary decision. Okay. The second binary decision is XSP, which is 1 if student S is assigned to project P and 0 otherwise. Okay. So we need the algorithm has to tell you a particular student which project are they assigned to. This is the ultimately clearly I require a binary output. Okay. I have to tell every student you are going to get this project. That's the allocation. I'm going to provide this to all students. It cannot be a randomized, it cannot be a fractional solution. Okay. You have to tell the students which project they're going to do. Okay. So that's going to be a binary decision. Okay. So what's the optimization problem? You want to maximize summation across all students, across all projects, the utility, okay, which can be captured by just asking students to rank their projects. Okay, so you can get this from their rankings, okay, which students actually do, times the amount of the allocation. Okay, so this is like a total welfare objective. Okay, you're trying to maximize the total welfare of the students. Okay, you want to get maximum utility in the system. So that's a very reasonable objective. Okay, there are some other objectives which you can look at, which is fairness, and we can talk about that if you want. Okay, what are the constraints? XSP is binary for every S from 1 up to capital S, P from 1 up to capital P. YP is binary for every project. Okay. Okay. Every student has to be allotted to a project. So every student should be allotted to a project which will be captured by this constraint, right? If XSP is binary, and if I sum this up across all projects for any student, let's say the first student, I sum it up across all projects and I make it 1. And because the variables are binary, it has to be one of them, as the student has to be allotted to one project. What additional constraints do I have? I have the constraint that, and this is where the allocation problem is somewhat unique, because you have this multidisciplinary type nature. So you have these lower bounds and upper bounds. You have to, and you have to ensure that for every discipline, so these projects, no project will be scoped so that only students of a particular discipline can take it. So you'll never get a project where the lower bounds and upper bounds are 0 for 3 disciplines, and for the fourth discipline, it is some positive numbers. That means you have only students of one group allowed in that project. This cannot happen. So these projects are scoped so that for at least two disciplines or two pillars, these lower and upper bounds are positive. Okay. So how can you? So what happens is, so you want to ensure that the sum of XSP, sum across all students, okay, And just to illustrate the discipline of a student, so I'm just going to assign a index. Let's call this D of S. Okay. This is the discipline of student S. Okay, it's a known data, right? For every student, I know which pillar they are in. So, for example, if this student is, let's say, in the ESD pillar, the corresponding index here will be 1 for the student. It's just a number. Okay, it's just a data point. It tells you which discipline the student is. So, what do I want to do? I want to ensure that for every student, for all students of the same discipline, let's call it D. So D. So I sum across D of S equal to small d. So what is this doing? It is summing up for the pth project. It is checking all the students of a particular discipline. Let's say the ESG pillar. For this, if I allocate, these are all the ESG students who could have been allotted to project P. If D is 1, I want to ensure this is below the upper bound. Sorry, below the upper bound. Okay. And of course, the upper bound can be allotted. I mean, the upper bound is valid when only the project is allotted, right? If my upper bounds, if I don't allot a project, if I don't launch a project, I cannot allocate students to it. X should be 0. So if Y is 0, X has to be 0. There's a corresponding lower bound here. YP, this is for every P from 1 up to P and for every discipline. That's it. That's an integer program. You solve this integer program, it solves in about a minute or 2 minutes. Okay.
Why is not necessary to keep P in the optimization function?
Sorry?
Why is not necessary to have GP in the optimization function? In maths and the so in the first part, the objective.
The objective is a utility. So what is a utility? Think of it like every student gives the preference for a project. So for example, student 1, okay, might say that the top ranked project is, let's say, project 1. So let's say, so actually what happens is students rank roughly 15 projects. Okay, they have 60 projects. It's too much to rank. Okay, so maybe students like this project, so they will give it a rank of, let's say they give it a number 15. YP is not, I didn't understand the question. Okay, okay. So I'm not trying to minimize. Okay. So here I'm just trying to ensure I'm not trying to maximize or minimize the number of projects or anything like that. Okay. I'm just trying to maximize students' utility. If you want to have other constraints, you're right. I mean, you can debate on what is important constraints. No, do you want to launch maximum number of projects? That's a valid objective. And you can bring that into the objective if you wanted to. Then you will not take student preferences into account. You want to balance student preferences and the number of projects, you have to take some combination of that in the objective. That's perfectly possible. So you have to discuss this with your stakeholders, basically. Okay. The other nice thing about integer programming is you solve an integer program, and when you allow in practice, when you do it, suddenly somebody will say, can you also bring in this aspect of the problem? No, this company, for example, we have not offered their project for the last 3 years. We better offer a project to them. How do we do that? If I want to launch a new project, let's say I want to allocate a particular project, let's say P star. All I have to do is I have to put in a constraint saying, um, let's say Y of P star is equal to 1. I can force this as a constraint. Okay. So what you can do is, as and when stakeholders have some inputs, they want to change something in the formulation, you can just add an extra constraints if you want to. This depends on who, the people who are solving the problem. And these are easy to do basically on the spot. You can just add in constraints as and when what the stakeholders want. Like you said, I want to put in something else, that's fine. Okay. Okay. So that's an integer program. At least for about 5 to 10 years, this was being used to allocate students to projects here. Okay. I don't know of other methods which can do this till you see it in the IP lens. Okay. 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 There are many other examples, but I just want to give you an illustration. Okay. So what I want to do is I want to spend time with modeling today, but sorry, I want to talk about how do you form the strength of IP formulations. But I just want to do one more logical constraint Okay, I just want to show you one more modeling trick, because I found that this modeling trick is quite useful sometimes. Over time, later on, you might solve an integer programming problem. It might come up in your research or somewhere else, and you want to model, right? So you require to know some of the tricks out there. So this constraint, this modeling trick, I found it to be useful sometimes. So I just wanted to introduce it to you too. Okay. So suppose you have a binary variable y in 0, 1. Okay. And let's say I want to capture, suppose I want to model the following logical implication. If y is 1, then I want to ensure that a particular linear constraint, which involves, let's say, x, which is some other variable, I want it to be greater than equal to b. So I want to capture this. So y is a binary variable. What do I want to do? When y is 1, I want to ensure that this constraint is holding, is valid. Okay, it holds. Okay. So I want to model something like this in my optimization problem. Okay. We've seen something like this already when we did fixed costs, because in fixed costs, we were trying to ensure that, something like this we were trying to ensure basically. Okay. This is the same thing, by the way, as, okay, so how will we model this? So I just want to show you how to model this. So the trick is very simple actually. Okay. You have to just write this as, uh, I think in the notes I've done it with less than equal to. So let me just do it with less than equal to. Okay. You can do it with greater than equal to 2. Just negate the sign. Okay. So the way you can model this is, so to model star, all I will do is A transpose X less than equal to B plus M times 1 minus Y. What is M? Where M is a valid upper bound on the difference A transpose X minus B. So, no, there are some variables X in your problem. There is some constraint A transpose X less than equal to B, some large enough number so that the difference of A transpose X and B is always below M. Okay, I'm sure about this. Okay. Okay. So why is this true? Okay. So let's think about what happens. So when y is equal to 0, what happens? When y is equal to 0, I get A transpose X less than equal to B plus M into 1 minus 0. Actually, let's do the y equal to 1 case first. When y is equal to 1, I get 1 minus 1, which of course is 0, which is B. So I'm getting my implication. When y is 1, A transpose X is less than equal to B. It's satisfied. When y is 0, I don't want anything, I want something redundant to happen. Okay. I don't want to force any implications, because this doesn't tell me anything about what happens when y is 0. When y is 0, I don't want to force anything. Okay. So the way you'll do this is, what happens when y is 0? A transpose X is less than equal to B plus M into 1 minus 0. But this is simply the same thing as saying A transpose X minus B is less than equal to M. But that's a valid already a upper bound basically. So this constraint is redundant. Okay. It tells you nothing more. Okay. So for example, if you know some bounds on X's, you can easily find some valid upper bound, or just make M some very large number, positive number. Okay. So when you're doing logical implications, you want to be careful. You don't force constraints beyond what is expected. You're trying to model this logical implication. So this will be the way to model it. Clear? Okay. But you can also say, I want to do the reverse modeling. Okay. I want to model. So this is modeling in this direction. Suppose I want to model the reverse implication. Okay. The reverse is not. So I want to model the fact that if A transpose X is less than or equal to B, then Y is equal to 1. Okay. So sometimes you might only have to model this. Sometimes you might only have to model this. Or sometimes you want to ensure both of these hold. That means every time Y is 1, you want A transpose X to be, so it's basically equivalent to each other. Okay. So how will you model this? Okay. So you require some additional, you require something additional here. So the way you'll model this is the following. Okay. So observe that this is the same thing as saying Y equal to 0, because Y is binary. If Y is not equal to 1, so if I take the reverse implication, it simply says A transpose X is strictly greater than B. Okay. These two are equivalent to each other. Okay. A implies B, not B implies not A. Okay. Okay. So if you want to capture this, the way you'll do this is the following. Okay. So this was star, equivalent for star. These two are the same. So for double star, all I will do is I will write it as, so of course your Y is 0, 1. Huh? So here what I'll do is A transpose X is I want to be greater than B, so I'll make it greater than or equal to B plus. I'm going to create. I'm going to use a lower bound. I'll tell you what this is. Okay, B plus epsilon plus small m minus epsilon y. Okay, so where epsilon. So what is m? M is now a valid lower bound on A transpose X minus B. So here we had an upper bound, capital M, big M. Here I'm taking a lower bound, some valid lower bound, and epsilon is basically a small tolerance. Okay. So basically, because if you think about this implication, y equal to 0 implies A transpose X greater than B. Okay. Strict inequalities we can't deal with in linear programming, right? We only have greater than equal to or less than equal to or equality. We never have strict inequalities. So basically, this to capture the strict inequality idea, you need some small tolerance, which basically beyond which A transpose X um, beyond which we are sure that A transpose X is greater than B. Okay, and I'll show you an example. But basically, the easiest way you can think about this is suppose suppose everything is integer. Okay, A is integer entries, B is integer. Okay, and let's say X is integer. So everything is integer valued. Okay, all these are integer valued entries. If I have some integer number to be strictly greater than some other integer, if I want to make greater than equal to, I simply have to set epsilon equal to 1, right? If something is greater, an integer is strictly greater than 4, the smallest tolerance is 1, 5 or more. Okay. So there's a smallest tolerance, epsilon equal to 1. Okay. So how do you model this? So I'll show you the model. The model is the following. You basically model it using this constraint. So I just showed you the constraint. Let's go through the logic. So what happens when y is 0? When y is 0, let's take this constraint. When y is 0, A transpose X is greater than equal to B plus epsilon plus M minus epsilon times 0. So this becomes 0. Okay. This becomes B plus epsilon. Okay. So if I wanted it to be a strict inequality, but strict inequalities, I can't make it hold in linear programming or integer programming in principle. So for an integer programming problem, where let's say everything is integer, if I say an integer value is strictly greater than some other integer, I simply have to say it's greater than equal to the integer plus 1. So I can set epsilon to be 1. So this is the same thing as saying A transpose X is strictly positive, strictly greater than B. Can you see that? And when y is 1, I want something redundant. What happens when y is 1? A transpose X is greater than B plus epsilon plus M minus epsilon times 1. Epsilon and epsilon will cancel. I'll be left with B plus M. So this is the same thing as saying A transpose X minus B is greater than equal to M, but that's already a valid lower bound. So this constraint is redundant. I'm not adding any new information basically. Okay. So the claim is that this logical implication can be modeled using this trick. This logical implication, which is equivalent to this logical implication, can be modeled using this trick. Okay. Again, once you see it, it should be quite clear. Okay. Maybe if you don't, this is where modeling becomes important. So you've got to see this sometimes to, I found this quite useful. Sometimes it shows up. Sometimes you have to model things logically. So this becomes a useful trick to know. Okay. Okay. Good. Any questions here? Was it clear? It's a trick, right? It's like a trick, basically. It's a modeling trick. It works. It's a linear constraint. So all these epsilons and small m's are constants. Big M is a constant. So these are just linear constraints with integer variables. So it's mixed integer linear programming. As long as you can get some estimate on the small m and big M and epsilon, you can use this basically. Okay. So when you model problems, sometimes you'll have to use these things. So I just wanted to introduce it to you. Okay. Okay, good. Uh, any questions before I change track a little bit? Okay. So our next goal will be to start thinking about the strength of mixed integer linear programming formulations. Okay. How do you know if a mixed integer linear program that you have written is a good formulation or no? What makes a good formulation? Um, it's not as trivial, it's not as easy as linear programming. Okay. And so we'll discuss this. Okay. So you've got an IP. Okay. So let's say I've got a mixed integer linear program, and let's keep a minimization problem to keep things simple. Okay. Let's say I've got a problem of this type. Okay. Let's say this is the problem. It's a mixed integer linear program. Okay. If I don't, if there is no, if you, the first approach that most people will think about solving the problem is just solve the linear programming relaxation. Forget integrality. Just solve a linear program. Okay. Just forget this. Okay. Just drop this. Why integer? Okay. Just solve the LP relaxation. Why is that a reasonable idea? Linear programming is solvable in polynomial time. We have very, very efficient algorithms for linear programming. So it's the first thing anybody would think about. Just solve the linear program. If your values are, I mean, maybe you can do some rounding, maybe you can round things up. You can do it. It doesn't always work. We'll see. Okay. But if it works, um, I can at least work with the LP, and maybe if I'm lucky, the LP might give me the IP solution. So the first and the most natural idea is to do a LP relaxation, okay, which is to minimize C transpose X plus D transpose Y, subject to AX plus BY equal to B, let's say X non-negative, Y non-negative. And what do I know about the optimal values of these two problems? Let's say this is the optimal value is ZIP star. Let's say this is ZLP star. Optimal values. How are these two related to each other in general? Which one will be higher? Will the LP optimal value be higher than the IP, or the IP optimal value be higher than the LP? Which one will be higher, the optimal value? Same constraints. I've only dropped, I'm dropping constraints. So I'm making the feasible region bigger or smaller. If I drop constraints, I'm not constraining, I'm giving you more options. Okay. So there's a lot more there's a lot more space here to optimize than here. Okay. You have a bigger feasible region here compared to this. Okay. So this is called a LP relaxation. So Z of IP star, okay, it's a minimization problem, right? And I'm minimizing here. Huh? So I'm minimizing over a larger feasible region. So the optimal value has to be lesser. Is it clear? If it's maximization, the inequality will go the other way. So you have to analyze the problem. Okay. So my natural technique, and in fact, most solvers, what they do is they first, when they are taking an IP formulation, they first look at the LP relaxation and solve it, and then try to do stuff with LP relaxation. And we will see this when we do cutting plane methods, when we do branch and bound next class. Okay, but so if a LP relaxation of a MILP formulation uh, is close, uh, if LP relaxation of MILP formulation gives values closer to the IP, it's a better formulation, right? It's a better formulation. So if I give you two different, and I'll show you an example, I'll show you a few examples today, but if I give you a LP formulation, and if the LP formulation has a value, optimal value, which is closer to an IP as compared to some other LP formulation, then that LP formulation should be a better value formulation, because it's a, I mean, that formulation should be better because my LP relaxation I can solve efficiently. Okay. So let's take an example just to make this point clear. Okay. Let's say I give you a IP. Okay. And the constraints do not matter. I mean, okay, it matters. But let's say these are all my integer programming. Let's say in two variables. These are all my integer points. Okay. Okay, these are all my integer points. Huh? So lattice. Okay. Okay. Left take. Let's say I've got a formulation, a linear, a formulation where I give you linear constraints. Okay. So this is a polyhedron. Okay. How many constraints are in the polyhedron? 1, 2, 3, 4, 5. Okay. So this is polyhedron P. Okay. So these are linear constraints. Okay. And for now, you can think of this as a pure integer program. Oh, what happened there? So think of this as a pure integer program. So there are no continuous variables. So in this problem, I've got essentially just variables x1 and x2. Okay. And I have got 5 linear inequalities which define x1 and x2. And I'm interested in points x1 and x2 which are integer within this set. Okay. So what are the integer points? This is an integer point. This is a feasible 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 point. So the black points are only my integer feasible solutions. Okay. The intersection of the polyhedron with integrality will give me these 5 points. Okay. That is one polyhedron. Okay. Let's call this polyhedron P. Okay. That's polyhedron P. Sorry, I just want to use the colors. Okay. So that's polyhedron P. Okay. Let's take a different polyhedron now. So here's a different polyhedron. Huh? I'll give you another polyhedron now. Let me use a different, let's use black. Okay. Or let's use some other color. Let's use maybe green. Okay. So here is a polyhedron, a different set of constraints. This is also a polyhedron involving 4 constraints. 1, 2, 3, and 4. This is polyhedron Q. Can you see it? Huh? Okay. What are the integer points in polyhedron Q? They are exactly the same as the integer points in the polyhedron P. Both polyhedron P and polyhedron Q have the same set of integer points contained within it. Which is a better formulation? Which is a better representation of the integer points, P or Q? Q. It's much smaller than P. Q is contained within P. If I optimize, in fact, if I optimize a linear function over the polyhedron P, I will actually get integer solutions automatically. Why? Because the extreme points of this polyhedron are integer points. If I optimize over the polyhedron Q, if I optimize over the polyhedron P, if my objective function was let's say C, I'm trying to maximize and it's increasing in this direction, it would have given me this solution. That is not an integer solution. So I would have to somehow go from this and move. I would have to find that this is the optimal solution. How? Okay. So the point here is very simple. So here in this example, both P and Q are polyhedron, in fact, polytopes, they're bounded, and contain the same integer feasible solutions. So if I was to solve a mixed integer linear program over these two sets, it's the same set of integer points. So both are valid IP formulations for my problem. If I was to use these 5 inequalities and say x is integer, it's the same set of points as saying these 4 inequalities and x is integer. But clearly, Q is much better than P. But Q is a much better, in fact, it is not only much better, it is the tightest formulation for this problem. It is a much better formulation, it's a much better formulation than P because it is Q is contained in P. Okay. Q is exactly the convex hull of the integer feasible solutions. Okay. So the name of the game in integer programming is to actually try to find the convex hull of the integer feasible solutions. And that is where the complexity of integer programming lies. If you can find me a good characterization of the convex hull of all integer feasible solutions, then I can solve a linear program over the set and I'm done. But to find this representation, of course, in 2 dimensions, I can do this. But imagine problems in high dimensions where you're given constraints and binary variables or integral variables. This is a very hard problem. But that's the name of the game in integer programming. And the last 50 to 60 years, people have worked non-stop to try to find representation of the convex hulls. Okay. Okay. Um, any questions here? Is it clear? I mean, this is at the key of integer programming. So you have to understand this idea. If you are not clear with this idea, I want to just stop a bit and just ensure it's clear. Okay. So basically, P intersection integers in this example is the same as Q intersection integers. I mean, in this example, it's Z2. Huh? It's just 2 dimensions. Both these sets, Q intersected with Z2 are these 5 points. P intersected with Z2 are these 5 points. Same points. But P is not equal to Q. Right? We have already seen, but Q is a subset of P. In fact, Q is precisely the convex hull of P Q is precisely the convex hull of Q intersected Z2 or P intersected Z2 because the convex hull of this set is precisely these inequalities. Okay. So if I can write the convex hull efficiently, I am in good shape. Okay. So if I was to optimize an LP over the polyhedron P, okay, and the LP over the polyhedron Q, the LP over the so in this example, like this ZIP is greater than equal to ZLP, right? If I solve the LP over the polyhedron Q, it would have been the same as the IP solution. But the LP over polyhedron P would have given a potentially smaller value. So you don't get tightness. Okay. Okay. Any questions there? Is it clear? Okay. So let's look at Uh, yeah.
Mhm.
Okay. So let's say I'm trying to minimize. Why will P give a smaller value? P is bigger than Q, and I'm minimizing over a bigger set. So in principle, so for example, let's say C is increasing. As an example, let's say C is increasing in this direction. I'm trying to minimize the objective. My optimal solution over P will be this point. But the optimal solution over Q, if this is parallel, it'll be both these points will be optimal. This will be a higher if it's increasing in this direction, it's decreasing in this direction. It's going to give me a smaller value than this. This is not a, I mean, this is not an integer solution. These two are integer solutions. So I'm far away from an integer solution in this problem. Okay. Q is a smaller region. So you are searching over smaller, fewer points. In P, you're searching over many more points. So the lesser constraints I put, the more freedom you have. So you can really go off and do anything you want. But if my problem is to find, I mean, my fundamental problem is to solve the integer programming problem. If that is my goal, then if I, if I mean, it's like saying uh, you don't put any constraints in, then there's almost no chance you're going to find an integer solution to the problem, basically, right? Yeah, is that clear? Okay. Um, okay. So maybe let me just so we'll come back to formulation, but let me just mention a couple of okay. So let's just sort of formalize this. Actually, okay, okay. So let's do the okay. Let's go back to facility location. Let's do this example, and then we can take a break. So I want to go back to facility location, and I want to show you two formulations for the problem, and I want to argue that both will give you the same integer programming solutions, but for one, the LP relaxation will be better. Okay. So here's formulation one. We saw this last week. So what? Sorry, on Wednesday. So what is a facility location problem? You got a set of facilities. There is a cost for opening a facility at every location I. So I goes from 1 up to M. There are clients J from 1 up to N. There's a cost for serving client J with facility I. So the formulation we saw the last on Wednesday was minimizing fixed costs for opening facilities plus the cost for serving uh, clients with certain facilities where yi was binary. This is exactly the formulation I did on Wednesday. So there's nothing new here. You serve each client with one facility. And then we have a constraint that says that if you open a facility, sorry, if you serve a client J with facility I, you better open facility I. Otherwise, you can't do this. So if Xij is 1, the Yi better be 0. Okay. Otherwise, it's not a valid formulation for the problem. Okay. And then we had a constraint that said that every client has to be allotted to one facility. So summation I from 1 up to M Xij was 1 for j equal to 1 up to n. So we did this. Okay. I showed you this formulation on Wednesday. Okay. So you remember this formulation? Is it clear what all the constraints are saying here? Okay. So this is what is called a disaggregated formulation. Okay. Disaggregated, disaggregated formulation for facility location. Okay. I'll explain why it's called disaggregated because I'm going to give you an aggregated formulation. Okay. So let's keep everything the same. Okay. So this is the objective. So here I'll give you an alternative formulation for the same IP. Okay. So I'm going to keep everything as is. Of course, I'm going to change something. That's why it's alternate. Okay. So I'm going to keep everything as is except one constraint. I'm going to change this third constraint, which said xij is less than equal to yi for every I and j. I'm going to change this constraint. Okay. I'm going to write this in a slightly different way. How am I going to? Oh, sorry. What happened to my? Oops. I want to keep both the formulations because we're going to compare the two formulations. Yeah. Okay. So what am I going to do? I'm going to take this formulation and simply write it in a slightly different way. Okay. And here's the way I'm going to write it. I'm going to sum this up. Sum xij uh, I from 1 up to so I want to do this for all j, right? So for every I, so I want j from 1 up to n, yeah, for all clients, less than equal to n times yi for I from 1 up to m. Okay. So let me just see if I can make it a bit smaller. Okay. So the only constraints which are changing in the two formulations is this third constraint. Everything else is exactly the same. Everything is precisely the same except for this third constraint. Okay. Okay. I claim that this formulation, which is called the aggregated formulation, is also a valid formulation for facility location. Why? What do you want in facility location? You want to ensure that if you're serving a client, the facility has to be opened, right? How many clients can a facility serve? It can serve up to n clients. Okay. So if any one, so what is the maximum value this Xij can take? It can go up to n. Okay, a particular client can serve up to n facilities, right? I'm sorry, a particular facility I can serve up to n clients. So at most, all of them, one facility serves all clients, if it's possible. Okay, that means at most this number can be n. Okay, so what happens when yi is 0? In the first case, all xij becomes 0. Similarly, when yi is 0, all the xij's have to be equal to 0. I'm adding non-negative numbers. Xij are non-negative numbers. They're binary numbers. I'm adding them up. If this number is 0, they better all be 0. I'm adding up non-negative numbers. If yi is 1, this constraint is redundant. It's saying that you can, if you open a facility, you can serve as many clients as you want. This constraint is the key constraint that you're trying to model, which both the aggregated and the disaggregated formulation are capturing. Is that clear? Can you see that both are the same thing or no? If yi is 0, all the xij have to be 0. If yi is 0 here, all the xij have to be 0. I'm adding up non-negative numbers, except I'm aggregating up constraints. In this case, if any xij is positive, if any xij is 1, the corresponding yi has to be 1. If any xij here is positive, the corresponding yi has to be 1. It cannot be that this number is positive and yi is 0. This constraint is not valid then. It's not correct. It's not satisfied. Okay. So both these IP formulations are the same. So I can call this IP1 and I can call this IP2. IP1 and IP2 have the same feasible region. Is that clear? But IP1 and IP2 look different. In one case, in IP1, I've got, forget all the other constraints, but I've got m times n constraints here. while IP2 has only M constraints of this type, right? So IP1 looks like a much bigger formulation than IP2. You have the same number of variables in both, but you have a lot more constraints in IP1 compared to IP2. M into N constraints. Here I've only got M constraints, right? IP1 is of a larger size than IP2. Okay, and you can precisely capture it, but basically there is order M times N constraints here. There are order Mn constraints here, and there are order uh, M constraints here. Is that clear? So the question is, you might automatically think this means IP1, IP2 is a better formulation. IP2 is fewer constraints and the same integer solutions. So maybe I should use IP2. It turns out actually IP1 is a better formulation. So size of a, okay. So is this clear, firstly? This part is clear so far? Okay. However, the claim is IP1 as a much better, as a stronger LP relaxation than IP2, making it a better formulation. Okay. So I'll show you why this is the case. We can take a break and maybe I can do it after the break. But the point is, if you look at the linear programming relaxation, this one has a stronger LP relaxation, which means that the feasible region of this set IP, the LP relaxation of IP1 is contained within the LP relaxation of IP2. Okay. And I will show this to you maybe after the break. Okay. So let's take a break. We'll come back in about 5 minutes. Okay.
No, I I say it is great. Yeah. There's two slides. I think there's nothing to be much. That we can use the previous one that we presented about. That's what I want. Yeah. I know. I will doing this in that manner. Yeah, I do the same. But the problem is that the time of the presentation is the same as my other class, not like 4 a.m. So it's like 4 to 5 on Wednesday. But I think it's not problem to leave earlier from your class. But I think the problem is that day in the presentation also. I see, I see. I think you may have to ask your professor to present after that. Yeah. Yeah, to finish the. Yes. And Would you are you planning whether once again in class or is a no? Either. Are you planning to enter once again in math or AI class or it was a no? I see no. But I may enroll this course next year or really. I'm not sure if I found other course that is more interesting and more direct to my research. I may enroll in that course instead. So the problem was the problem is that the professor begin to going a little bit lower to the classmates. They got a lot of questions and so now he is presenting half of the slides. He wanted to what's that? First of all, which will be the line. Shall we be unbeaten for 6 games in a row? Yeah. Yeah, we must be. We have to be. I want to come back. I love being we have passed the weakest point yeah. Of the club already. So, I think they will be this will be them. You know, most of things. Yeah. 2 more seasons. It's like yeah, like you see, if you look at when that's what they said came in coach, they were sort of in a very bad state. They came like six. Yeah, to bring them up. Yeah. So was still hope. Yeah. Amory will be the second solution. It's more for
Okay, shall we start? Yeah. Okay. So, just a quick reminder. Just I showed you two formulations for the same facility location problem. They look almost the same, but for one set of constraints, which is I'm this constraint where I want to ensure that if I'm serving a client with a particular facility, the corresponding facility has to be opened, can be modeled using disaggregated constraints or aggregated constraints. The integer programming solution for both of them will be the same. Okay. However, the LP relaxations, if I take these constraints being 0 or 1, and I relax it to saying it's between 0 and 1, the LP relaxations of these two problems may not be the same. Okay. So you can go back to thinking of this problem. The LP relaxations of both have the same integer set of integer solutions, but the LP relaxations are different. Similarly, this is of course in higher dimensions, the LP relaxations are different. I claim that the LP relaxation for IP1 is better than the LP relaxation for IP2. Why? Okay. Why? Okay. Why is this got a stronger LP relaxation than IP2? Okay. So remember, what are my constraints? My constraints are Xij is 0, 1. Now I'm thinking about LP relaxations, and these YIs are 0, 1. Okay. For the for IP1, my that corresponding linear constraint was what? Xij is less than equal to yi for every I and for every j. While for my aggregated formulation, my constraint was summation across all I equal to 1 to m. Sorry, I'm serving, I can serve all clients. So summation j across 1 to n xij should be less than equal to n times yi. Okay. The claim is if I've got a set of variables x's and y's which satisfy this constraint, they have to satisfy this constraint. So this implication has to be true. Why is this? This is straightforward. Why is this implication satisfied? If I give you an x and y which satisfy this constraint, and these constraints, this constraint has to be satisfied. Straightforward. Just sum this up. If you sum up over all j. If I sum this up over all j, what will I get? So if I sum up this constraint star over all j, what will I get? Summation j equal to 1 up to j, n, xij, less than equal to yi added up n times. So I'll get n times yi, which is exactly this constraint. So any x and y which satisfies this constraint will satisfy this constraint. But the reverse need not be true. Any x and y which satisfy these constraints, continuous variables, need not satisfy this constraint. Why is that? Here's an example. Let's take, I can keep things really simple. Take a single facility and maybe let's just look at a part of the problem. Let's say my yi variable here was, let's say, 0.3. Okay. So what is this constraint? So if n is equal to 2, what is this constraint telling me? This constraint is telling me x 1, 1 plus x 1, 2 should be less than equal to 2 times y2. Suppose y2 is, let's say, 0.3. Okay, so this is 0.6. So I could have had 0.4 here and 0.2 here in the LP relaxation for my for my aggregated formulation. 0.4 plus 0.2 is 0.6. It is less than equal to 2 times 0.3, which is 0.6. So this is feasible for this constraint. But this is not feasible for this constraint. Not feasible. Why? Because clearly xij is not less than equal to yi. So this A implies B, B does not imply A. So there are LP solutions for this problem which are not going to be allowed in this region. So this is going to be a much smaller region, that the disaggregated formulation. And this is exactly what you want. You want LP relaxations to be tighter and tighter. Take out things which are not, which are linear, which are fractional solutions, but not integer solutions. Okay. Is that clear? So there will be LP solutions to this problem, but are not going to be feasible for this problem. Though the IP solutions are same, this LP region is going to be larger than this LP feasible region. So therefore, uh, yeah. So therefore, the LP, this IP2 formulation is uh, worse off than IP1. Okay. And this tells you something about LP. I mean, if you think about linear programming problems, you would generally think fewer constraints, fewer variables is a better thing. This is true. But here I showed you an IP formulation where actually having more constraints was better because LP relaxation was stronger. Okay. So it is not as trivial formulating. You can't think of a formulation just in terms of sizes of variables and constraints. It's of course important, but you have to think about the strength of the LP relaxation. Is the LP relaxation good or no? Because most IP solvers require good LP relaxations. Okay. So is that clear? Okay. You can't go a naive way and just say smaller the size of the IP, it has to be better. This is not true. It's not like LPs. Okay. Okay. Any questions there? Okay. So what's an ideal formulation? So this we have already discussed, but let me just concretize this. So suppose I have got a LP. So let's say I've got an IP of this type, minimize C transpose X, subject to let's say AX equal to B. Let's say X is integer, X non-negative, X integer. Okay, and for completeness, let's assume, to keep things simple, let's assume that the feasible region is bounded. Okay, so I'm going to assume that the assume feasible region is bounded. That means no X value can go off to infinity. Okay. Um, it just makes it easier to write everything down. Okay. Okay. So suppose I want to solve this IP. Okay. So this is an IP. What is the ideal formulation? The ideal formulation is, if the feasible region is bounded, the set of IP solutions is what? It's a set X1 up to some capital XK. Okay. Because I'm looking at integer values solutions, there are only finitely many of them, and it's a bounded set. So no integer can go too large. Okay. So there is a set of solutions where essentially each of these AXK is equal to B, XK is non-negative, XK is integer, for K equal to 1 up to capital K. Essentially, this is a finite set. Okay. It's a finite set of solutions. Okay. So if I want to solve the IP, I could have actually solved the IP in a different way. If I know all these points, all I would have done is I would have basically minimized C transpose X subject to X in the set X1 up to XK. But if I want to minimize a set of points over, if I want to minimize a linear function over a set of points, that's the same thing as minimizing. This is equivalent to minimizing C transpose X subject to X in the convex hull of these sets, because the convex hull of these points, if I give you a set of points and I want to find the minimum over these points, I know that the convex hull of this set, which is a polyhedron or a polytope, the extreme points of this will be these integer solutions. But this is nothing but a linear program. Huh? A convex hull is basically just a set of a convex hull can be described by either a set of extreme points and you write a convex combination, or you write linear constraints. So in principle, every integer program can be solved. I mean, this is an LP problem. Okay. The convex hull of a set, you can describe this in many ways. One way, for example, is, what is a convex hull? It's basically the set of all lambda k xk, where lambda k is equal to 1. I mean, this is just a definition of a convex combination, right? And all these xk. So you can actually write any integer program as a linear programming problem over the convex hull of the feasible points. Okay. But finding the convex hull is not easy. Okay. And this is why I mean, another thing I want you to remember, and this is something because I've seen this very often, every convex programming problem is not easy in this world. Okay. That is, sometimes people tend to believe that if something is convex, it becomes easy. This is not true. The convex hull of the points has to be well understood. Okay. So this is a convex optimization problem. The challenge in this problem is writing this convex hull. You cannot write the convex hull efficiently for integer programs in general. Okay. So this becomes hard because this capital K is very large and you can't write the integer programming formulation, the convex hull efficiently. So the key is to find convex hull of integer feasible solutions. And this is what integer programming solvers work towards, trying to find the convex hull of all the integer feasible solutions. And this is the technique that we will see later on when we do branch and bound and cutting plane methods. Okay, is that clear? The basic rational logic, or okay? So here is a so let me give you an example. So sometimes there are sets, integer sets, where the convex hull is just the LP relaxation. So here's an example. Example. So in this example, let's say I'm given, say k is an integer between 0 and n. Okay. So want to describe the following set, capital X in 0, 1, n. Okay. Where the summation of x has to be equal to k. Okay. So this is a 0, 1 set. I'm taking all binary vectors where the variables add up to k. So for example, let's say n is equal to 4. Let's say k is equal to 2. What are the feasible points in the set? The feasible points are 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1. These are all four-dimensional vectors with binary entries where they add up to exactly k, 2. Exactly 2 are zeros. This is the set for n equal to 4 and k equal to 2. Okay. So this is an integer set. It's a set of integer vectors. Okay. The convex hull, so it turns out, and this is very easy to see, but the convex hull of this set. So what is the convex hull? You take all these points and you write all convex combinations of these points. You can write this in the following way: x between 0 and 1, where summation I equal to 1 to n xi is equal to k. This is exactly the LP relaxation of this set. X is either 0 or 1. I will say x lies between 0 and 1. And summation of xi equal to k. This is just linear constraints. There are non-negative variables, upper bounds of 1, and the variables add up to k. The convex hull of this set is exactly this set. So what is the advantage of this? If I want to solve, so I'll tell you why this is so okay. Let's first look at why this is the case. Why? Okay. Think of what a basic feasible solution. So this is a set, right? This is a polyhedron. Okay, what is this polyhedron? Xi between 0 and 1 and sums of xi is equal to k. So why? So what does a basic feasible solution look like? An extreme point of this polyhedron is a basic feasible solution. What's a basic feasible solution? Let's go back and remember LPs. N linearly independent active constraints at that point, where n is the number of variables, and it should be feasible. So a basic feasible solution requires n linearly independent active constraints at x, and x should be feasible. Okay. So I require n linearly independent active constraints, n, okay? So let's say n is equal to 4. I've got one constraint here. The remaining three constraints have to come from this 0, 1. So either xi, so what are these constraints? Xi is either 0 or 1, right? I can write this as all x in Rn, xi between 0 and 1 for I going from 1 up to n. That's the LP relaxation, right? So n minus 1 constraints have to come from here. They have to be tight. What does that mean? Xi has to be 0 or 1. What does it mean to be tight? It forces xi to be either 0 or 1. So n minus 1 variables. So therefore, at a basic feasible solution, n minus 1 of the xi variables is either 0 or 1. 0 or 1. And the last variable, so I've got n variables, n minus 1 have to be 0 or 1 at every basic feasible solution. The last one is obtained by this constraint. But k is an integer. If I'm adding up integer entries and it has to be equal to some integer entry, the last variable also has to be integer. Right? I cannot add up integer numbers and add some fractional number and have it to be equal to an integer number. So the last variable also has to be integer. Last variable also has to be integer because k is integer. And these integers are between 0 and 1. So every integer has to be either 0 or 1. There's nothing else possible. There's no other integer between 0 and 1. Okay. So every basic feasible solution is 0 or 1. And I mean, the values are 0 or 1 and they add up to k. But that is precisely the set. You're done. So for this problem, if I want to solve this this IP, suppose I tell you, solve this IP. You should not solve this as an IP. You should solve an LP and solve this problem. You're done. This is exactly the same as minimizing C transpose X subject to X in 0, 1, N, where summation I equal to 1 to N Xi is equal to K. So this is a problem where the LP relaxation gives you exactly the integer programming solutions and you're done. And IP becomes an LP solution because the convex hull of this set is precisely defined by the LP relaxation. So here, the convex hull of the integer feasible solutions, okay, is precisely the LP relaxation. Okay. So there are problems where the LP relaxation will be tight, but many integer programs will not have the structure. Okay. And what is this problem doing? If you just think about, I mean, what exactly is this problem doing? You're trying to minimize. If you think about what this problem actually is doing, you've got numbers C1 up to Cn. I'm trying to pick, if you think about what this problem exactly is doing, it's trying to pick the k smallest numbers. It's saying that you sort these numbers from small to high. You sort these numbers and pick the k smallest. Okay. So this is a problem in what is called order statistics. It's a problem in stats. Essentially, if you want to pick, if I give you n numbers and I ask you to pick the k smallest or the k largest numbers, you can write that actually as a linear programming problem. It's precisely this. Okay, you can minimize or maximize depending on you're trying to find the k smallest or k largest numbers. Okay, again, you cannot enumerate because the number of feasible solutions for this problem is n choose k. Okay, so if n is 100, k is 50, that's 100 choose 50, that's exponentially large. But an LP with exactly 2n plus 1 constraints solves this problem. Okay. Okay. Any questions there? It's a very useful problem. It's also called, by the way, it is also called the, if you have less than equal to also you can do, it's called the uniform matroid. It's not critical for you, but this set is a very useful set to know. Okay. It shows up a lot because uh, it's basically like out of n entries, you're trying to pick k of them. Okay. And there are many problems where you're trying to choose out of a set of many entries, a subset of them of cardinality k. This is exactly that set. Okay. Okay, good. Um, any questions here? You've gone very quiet. I'm just worried if I'm losing you or it's all very obvious. Was it clear why the extreme points of this, why the extreme points of this set are binary? Was it clear or no? The logic. Okay. Okay. Fine. Okay. So the for the last half an hour, I want to just discuss IPs that have. So I want to show you a few more IP formulations. Okay. The interesting thing here will be with exponentially many constraints. Okay, and I will. There are many problems where the natural integer programming formulations have exponentially many constraints, and you can still maybe do something about it. Okay, so I'm going to show you today a spanning tree, traveling salesperson, and perfect matchings. We'll see how far we can go. Okay, so the first problem, it's what's called MST, minimum spanning tree problem. Okay, so this problem we have not, I don't think we have done the minimum spanning tree problem. We have seen spanning trees when we did the network simplex method. So when we solve minimum cost flow problems, we saw that every basic feasible solution is a spanning tree solution. But now we are going to take a problem called the minimum spanning tree problem and try to solve it directly. Okay, so what's the MSC problem? So I'm given undirected graph and edge costs, CE. Okay, so for every edge, there's a cost. Okay, find a spanning tree, spanning tree of min cost. Okay, so what's a spanning tree? We have discussed this. A spanning tree is a graph that connects all the nodes and there are no cycles. So it's the sparsest connected graph. So if I give you a set of nodes, it's the sparsest graph that connects all the nodes. Okay, so I want to find this of minimum cost. Okay, so for example, if let's say this is a graph, let's say there are some costs. So one spanning tree on this graph is, that's a spanning tree. The cost of this spanning tree is 1, 4. So the cost of this spanning tree is 4 plus 2, 6 plus 2, 7 plus 1, 8. Okay. Here's another spanning tree. I think this is minimum spanning tree. 1, 1, 1, 2. This spanning tree has a cost of, sorry, this spanning tree has a cost of 1 plus 1, 2 plus 1, 3 plus 2, 5. And I claim actually this is the minimum spanning tree on this graph. You can actually use a greedy algorithm to solve this, but that's the minimum spanning tree. Okay. So the minimum spanning tree problem clear what the problem is asking you. Okay. Okay. You don't have to, I mean, You can check that there'll be no other spanning tree which is smaller than this cost. The algorithm is not important. What I'm interested in right now is how to write this as an IP. Okay. Okay. So I'm going to show you a couple of formulations. Okay. So what is the natural variable in spanning tree? You take an edge of the graph. Should it be in the spanning tree or no? Okay. So the variable xe will be 1 if edge e is in the spanning tree. If edge e is contained in the spanning tree T, and 0 otherwise. Okay. I mean, this is the natural variable for a spanning tree problem. Okay. So the first formulation, formulation 1, is to minimize the total cost across all edges. So if you take if you take a particular edge E in the spanning tree, you pick up the cost of CE, subject to you decide to either keep a edge or not keep it in the spanning tree. That's a binary variable. The next thing a spanning tree has to satisfy is the total number of edges which have to be picked up in a spanning tree. So let's say the number of nodes in my graph are n. Every spanning tree will have how many edges? N minus 1. If you have more than n minus 1 edges, you will definitely have a cycle. Okay. So you require the total number of edges to be n minus 1. Okay. The challenge if you only use this formulation is you can have cycles. Okay. So you could have, if you only have those three constraints, those two constraints, the binary variables and the fact that they add up to 1, I could have chosen, for example, 1, 2, 3, 4. I could have chosen a solution like this, which is clearly not a spanning tree. Okay. How many arcs are chosen? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But this is clearly not a spanning tree. So something is not being captured by these constraints, which I have to worry about. Right. So this is not sufficient. Something more is required so that I'm capturing the set of spanning trees. And that is called, there are two ways to do it. One is what is called the subtour elimination formulation or the cut set formulation. Okay. So let me first do the subtour elimination formulation. Subtour elimination formulation. Okay. So what is the subtour elimination? If I give you, intrinsically, it's quite straightforward. If I give you a set of nodes S, okay, and I take the edges which go within this set, okay, let's say there are 4 nodes in the set S, and maybe these are the edges which are allowed, which are edges in my graph. I have to ensure that for all the edges in this set, so what is called the edge set, okay, so this is called the edge set. Okay, what is the edge set? I can define it. E of S are all the edges in the graph where I lies in S. I'm sorry. All the edges in the graph, it's an undirected graph. All the edges in the graph such that both I and J lie in the set S. Okay, so I might have some other nodes outside. So the edge set are only these set edges. Both the nodes, both nodes have to be in the set S. Okay. So what is this telling me? The total number of, I look at X plus this X plus this X plus this X plus this X. It cannot exceed S minus 1, the size of the set S minus 1. Why? Because within a subset of nodes, let's say I've got 4 nodes. If you choose 4 arcs, you're dead. You've formed a cycle. You have to choose 3 or fewer arcs. for every subset of nodes, which is a subset of V. So when S is equal to V, these are all the edges. So I'll get this constraint. Of course, S is not empty set. This subtour elimination prevents solutions of this type, because if I look at the subset of nodes, if I chose this subset of nodes, what are my edges in this subset? It's basically this edge, and this edge. So I want this x plus this x plus this x to be less than equal to the cardinality, which is 3 nodes minus 1, that's 2. The sum of these three has to be less than or equal to 2. I cannot have 1, 1, 1. Not allowed. It prevents subtours, basically. Okay. This constraint is very important. It will show up also for the traveling salesperson problem. It's called the cut set formulation. The subtour elimination formulation. It turns out if you solve this integer program, you solve the TSP problem. In fact, if you solve the LP relaxation of this problem, you also solve the TSP problem. Okay. Is the formulation clear? The challenge in this formulation is what? If you just look at this formulation, what is a computational challenge? Number of subtours, the number of constraints, exponentially large. Because what are we doing here? We are taking every subset of the vertices. I don't know beforehand where the subtours are going to be formed. When I'm solving an LP relaxation, I don't know if my subtour will be in these nodes or this node or this node. So I have to ensure that these subtours are eliminated throughout. So what I have to do is I have to write down these subtour elimination constraints for everything. Okay. But this is where, if you remember the ellipsoid method, just because you have exponentially many constraints, the problem doesn't become hard. It turns out that the separation problem here is easy for this problem. If you just write down the naive formulation explicitly, it is too large, this LP. There are too many constraints. But you don't have to solve this LP in one shot by writing down all the constraints. You basically can just solve the problem with the dropping these constraints at the start. Check if your solution has got. So how you solve this is, the way you can solve this is, let's say there are constraints, like solve the LP relaxation without subtour elimination constraints. If you're lucky, you'll find a TSP tool. Okay. You'll find an MST tool. If you find MST, if you find a spanning tree, if you find a spanning tree solution done. If not, you will obtain a subtour. Okay. You will obtain a subtour like this. Like, you might have found that some of these, there's a set of X values where they form a tour. So you have to then put in the constraint explicitly. So you have to go and say x plus x plus x, these three x's have to be less than equal to 2. So you have to add in a constraint. This is exactly what is the separation problem. And you can do this in this case by solving a min cut problem. Okay, I won't go there for this course. Okay. Okay, there's a second formulation for this IP. Okay, so you can basically you add in corresponding subtour elimination constraint. Okay, and resolve, and you can basically do a resolving algorithm. Okay, okay, fine. Any questions there with the formulation? Okay, I want to show you a second formulation. This formulation is what is called the cut set formulation, formulation 2. Okay. Everything is the same, except we are going to force these constraints in a slightly different way. Okay. Okay. So everything is going to be the same, but for this last constraint. How are we going to do it for the sub two, the cut set formulation? So this is called the cut set formulation for MST. Okay. It's an idea that I think we have seen before, which is you're trying to ensure there are no subtools being formed. That means in that example I showed you before, the problem is what? When if you have a solution of this type, the problem is there is no edge going out which has a positive value in the solution. So the way you can do this is you can ensure that when you look at summation xe, E in delta of S. So this is the cut set. Okay, so what is delta of S? It's called the cut set. So if I take a set of nodes S, it's all the edges in the graph. So all the edges in the graph such that um, I lies in S and J does not lie in S. Okay. So if you look at, let's say if this is a set S, and let's say these are edges which are there in my original graph. That's these two nodes form my delta of S. What my cut set formulation is going to say is you cannot, if you take a subset of nodes and you look at the edges that come out of this set S into the S bar, the complement set, at least one of them has to be one. So at least one, there has to be something flowing out of this set. Otherwise, you're going to have these subgroups being formed. This is for every set S not empty. So it is capturing the same subtool elimination. What it is doing is it is not going to let you have solutions like this where both of these numbers are zero. This cannot occur because if you look at this constraint, it will be violated because the edges coming out of this set are this edge and this edge. They two add up to zero, which cannot be true. So the cut set formulation is an alternative formulation for the MST problem. Okay. Any questions here? Is it clear? Okay. Okay. So, good.
How do you find data, data?
Delta S is just what is delta S? That means delta S is simply so if I give you a graph like this, one, two,
No, but I mean, delta is fixed or you can
for
use.
every set S, there's a particular delta S. For every
Okay.
set S of nodes, you find the edges that are in that go from S to S bar, which you can, of course, again, this is exponentially many. You have the same issue here. Okay. You have the same issue here, basically. But in principle, you can write down this. Again, it turns out you can solve this problem. You can do the separation idea. Okay. 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 I think I'll do. I'm trying to figure out which one should I do. Okay. Maybe I'll just do this. Uh, I'll do this argument and then we can stop for today. So, okay. So so I want to show you another example like the aggregated disaggregated formulation. So let P sub and P cut be the LP relaxations of the subtour elimination and cut set formulation of MST. LP let be the feasible be the feasible region of the LP relaxation. So it's a polyhedron. Okay, so all I'm doing is I'm taking these two problems. I'm forcing XE is binary. I'm just going to say XE lies between 0 and 1. They add up to n minus 1. In one case, I'm going to say the total number of edges in the subtours, you can't have cycles within a set. In the other, I'm going to say you have to have at least one edge coming out of a node which is in the which has to be greater than or equal to 1. Okay. Both of these are exactly give the same TSP sorry, MST solutions. Okay. If I was to relax the integrality restrictions and just solve the LP relaxation, you'll get two sets. So here's a theorem. Which formulation is better, subtour or cut set? It turns out the subtour formulation for this problem is better than the cut set formulation. That means that's a smaller set. The LP relaxation of that set is tighter than the LP relaxation for the cut set. Okay. So I want to do this argument and then we can stop for today. Okay. So is it clear what the theorem is telling you? The IP solutions for both problems are same, but the LP relaxation of the subtour formulation is contained within the LP relaxation of the cut set formulation. That means the subtour formulation is actually a better formulation. Okay. So that's the theorem. Let's try to prove that. Okay. Again, this is a type of proof you often do with these cuts formulation. Okay. So they were basically going to do a counting argument. Okay. So you've got a set S, you've got a set S bar, the complement set. Okay. What are the different edges? There are edges that connect the nodes in the set S. Okay. So all of these are the sets which I call the edge set S. Okay. All of this is E of S. I've got edges in S bar. Okay. This is E of S bar. And then I'm going to have edges that go across my graph from maybe S to S bar. I don't know, maybe something like this. All of these are delta of S. Okay. These two, E of S and E of S bar, show up in the subtour elimination formulations. Delta of S shows up in the cut set formulation. Okay. So if you look at, is it clear what I'm counting here or no? Okay. So for any set of nodes, subset of nodes of the total edge, so I take all my vertices, I take any subset of it, strict subset, not empty. Okay. The edges in the graph, all the edges in the graph is either going to be edges contained within the set S, that means edges connecting the nodes in S, all the edges connecting the nodes in S bar, all the edges that go from S to S bar. Okay. And these three sets are disjoint. So I'm just counting three different sets. Okay. Is it clear what I'm doing so far or no? Okay. Then think about now for every edge, there's a variable XE. So when I write summation of XE, E in the edges, this will be summation of XE, E in the edge set of S plus, because these are disjoint sets, all the edges here will have a corresponding X variable. I'll add up all of them. It'll either be in this set or in this set or in this set. Okay. Okay. So from this, I get this constraint. These were the same thing basically. Okay. Okay. Now, what do I want to show? I want to show that subtour is contained within cut set. That means if I take a point in this set, it will be a point in this set. Okay. So so given x star, let's say, or given some x, actually not x star, any x in P sub, okay, what do I know? I know something about how the x's look like for E of S. Okay. I know that because this is a point in this set for the LP relaxation, these constraints have to be satisfied. So I know what? I know that this part is going to be lesser than equal to S minus 1. And this part has to be lesser than equal to S bar minus 1. Yes? Because the point in that set, it has to satisfy. This number has to be less than equal to S minus 1. This has to be less than equal to S bar minus 1. So I have to tell you something about what will happen to this one. Okay. So if I just write this down, summation, and what is the total number of edges in the graph? For the total number of edges might be any number, but if I add up all the x's over the all the edges in the graph, what do they satisfy? N minus 1. So for any solution in this subtool elimination formulation, this number will be exactly n minus 1. This number will be bounded from above by s minus 1, the cardinality of s minus 1. This number will be bounded from above by cardinality of s bar minus 1. So this will tell me something about this. Okay. So this number, n minus 1, will be lesser than equal to s minus 1 plus s bar minus 1 plus summation xe E in delta of s. Just move things around. Move this entire thing to this side. And what do I know about S and S bar? It's all the nodes in my graph. So these two numbers add up to N. So these two are exactly N. They cancel out. There's a minus 1 cancels out. I'm left with a single minus 1 here. So therefore, summation XC E in delta of S is greater than equal to 1. But what is this constraint? It's exactly this constraint. So any solution for the subtool elimination formulation will actually automatically satisfy the cut set elimination formulation constraint, the cut set formulation constraint. Okay. So therefore, if X lies in P sub, X lies in P cut, which means that this should be a better formulation. Okay. Now it turns out this is not true in general. You can find points which lie in this set and not in this set. Okay. Maybe I'll just show you an example very quickly. Okay. That means the reverse implication need not be true. I'll show you an example just to illustrate this. So let's say it's there in the textbook, but I'll just show this to you quickly. Okay. Um, so here is a um, uh, 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 so here is the solution. So it's a okay. So let's say I give you a solution which is actually yeah. So let's say the solution here is the flow is 0 0.5, 0 0.5, 0 0.5, 0 0.5, 1 and 1. Okay. Okay. How many nodes are there? 1, 2, 3, 4, 5. Okay. Are all the variables between 0 and 1? Yes. Okay. So every xe is clearly between 0 and 1. Okay. The sum of xe's is what? 0.5 plus 0.5, that's 1, plus 1, 2, 3, 4 is equal to 4. How many nodes are there? 1, 2, 3, 4, 5. N is 5. So it satisfies this constraint, the first constraint. Okay. Now, let's look at whether it satisfies the cut set elimination constraint or no. Okay. So if I look at a point, if I look at let's say 2, 4. So let's look at maybe this particular set S. Let's look at this S. Okay. What is the cut set formulation telling me for the edges coming out of this set? That's basically this edge and this edge. It adds up to 1. So summation of XE for E coming out of this set is equal to 1. So it's valid for the cut set formulation. Okay. So it turns out this solution lies in P cut. Okay. You can check. But this same solution does not lie in P sub. Why? Add up these three edges arcs costs. 1 plus 1 plus 2.5, sorry, plus 0.5, which gives me 2.5. What is the cut set formulation? The sum of these three has to be less than equal to 3 minus 1, which is 2. But this number is more than 2. So this point, X, is not in P sub. So you have points which are in this set, but not in this set. Okay. So, I mean, you might have, one might think that the reverse implication is also true. It's not true in this problem. So it's not only that P sub is, so it's not just that P sub is uh, so there are basically there are instances where P sub is strictly within P cut. Okay, it's a strictly better formulation, basically. Like here's an example, right? I've got a particular feasible LP feasible solution, which is feasible for P cut, but not feasible for P sub. Okay, is that clear or no? Did you see why? Could you make out why this is not feasible for P sub? It violates this constraint. It violates the constraint. It violates this constraint because S is of size 3. This should be less than equal to 2. But in this point, this particular solution, it adds up to more than 2. However, this you can check. This is always going to be valid for P cut. Okay. So this is how you compare IP formulations. You take a solution to one problem and check if it is feasible for the other formulation, the LP relaxations, and then you try to get an ordering of the LP relaxations. Which LP relaxation is better? Okay. Okay. Let's stop today, and I'll see you next Wednesday. If you've got questions, you can ask me. Otherwise, I'll see you on Wednesday. Yeah.